Okay, welcome to the lecture here. We'll continue on and pick up where we left off last time. Move some things around here so I can actually see. Let's see. There we go. So we're going to kind of finish up chapter 4, I think, and then we'll probably roll into some chapter 5. Again, the notes are up there on Canvas if you need them. Okay, so we've been talking about bonding, and at the beginning of this chapter here, chapter 4, kind of a continuation of chapter 3, sort of in the bonding and the Lewis structures. We talked about, again, different types of geometry, and we talked about electron pair geometry, molecular geometry, again, and some of those new ones probably for a lot of you, which is those ones that cover sort of the expanded octet, the ones with 5 electron pairs and 6 electron pairs around it. So we got some new sort of geometries happening there. And then we got into the idea of hybridization that we were talking about last time. And hybridization is sort of a bonding theory that basically results from taking atomic orbitals. And when we talk about atomic orbitals, those are our s orbitals, our p orbitals, our d orbitals, our f orbitals, and basically comboing together a mixture of, say, an s orbital and some p orbitals, a mixture maybe of some s orbitals, p orbitals, and d orbitals. And what these make is what are referred to as hybrid orbitals. And sort of the advantage of hybrid orbitals is the idea that instead of taking just the atomic orbitals by themselves, where you have basically, in theory, sort of different shapes, like a sphere for a s orbital, sort of a figure 8, if you will, for a p orbital, and that those orbitals are all sort of in different bits of energy in terms of their levels, and trying to mix those guys together to make bonds. What we have here is the idea of hybridization that makes basically equivalent orbitals, and these are equivalent hybrid orbitals that essentially have the same sort of shape. They're also equivalent in terms of their energy. And what that allows for is this idea of sort of better overlap and better sort of bonding to occur, and also sort of accounts for the geometries that we see, the bond angles that we see in some of these molecules. And the easiest way to sort of figure out hybridization, I know last time we went through a lot of sort of arrows, boxes, all those kind of ways of doing it. And again, that was just to kind of show you the bonds and illustrate sort of what's happening with the bonds and stuff like that. The easiest way to do it is really hybridization is tied to the electron pair geometry. So when we talked about geometry and those electron pair geometries, there's essentially 2 electron pairs, 3 electron pairs, 4 electron pairs, 5 electron pairs, and 6 electron pairs. And when you go to try to identify sort of hybridization, what you want to do is essentially kind of count everything like you're doing geometry. So what that means is if you have a Lewis structure that you drew and you still have a double bond or a triple bond that happens to be there, you would still count it as only 1 electron pair. So really, in sort of doing hybridization and also doing the geometry, you want to count the total number of electron pairs really the same way. So double bond, triple bond counts as only 1 electron pair. And as I did a number of times the other day when we were kind of going through it, really the simplest way to do it is you could just draw yourself, there's only 1 s orbital, there's 3 p orbitals, and we won't get anything past d, so d orbitals. And really, once you figure out the total number of electron pairs, you pretty much can count off the hybridization by always starting at s. So you always start down here. So for example, like we did up here with this carbon, what we'd want to do is just figure out the total electron pairs. So 1, 2, 3, and 4 electron pairs. So if I wanted the hybridization, again, starting with s, 1, 2, 3, 4, again, I use 1 s orbital and 3 p orbitals, and that is how we got to the sp3 hybridization for that particular one. Again, same thing as we talked about when we have something like a double bond like we did on the other end of this molecule. Again, we would look at this carbon here, and it would have 1 electron pair, 2 electron pairs, and again here our double bond only counts as 1 electron pair. So that would be 3 electron pairs. So 1, 2, and 3, that's an S and 2 Ps. So again, just sort of the easiest way to sort of figure out hybridization really quickly, going from your properly drawn Lewis structure. The simplest way to do is really just to count electron pairs. Again, the same way that you would do geometry. And that will allow you to apply hybridization to pretty much anything. For the most part, you can even apply hybridization like we did, for example, to this oxygen up on top. And again, you would do the same thing. So even if there's not bonding electrons, but non-bonding electrons, you count them. So that would be 1 electron pair there, 2 electron pairs there, and again, our double bond counting as just 1 bond, and that would basically be 3 as well. So 1, 2, and 3. Again, an S and 2 Ps that basically came together will give you your hybridization. So in all my years, that is the simplest way to pretty much figure out hybridization really quickly. And same thing where we have like the carbon here, this is going to be our 1 electron pair here because it's a double bond, and 2 electron pairs on the other side. And again, 1 and 2, that's an S and a P, gives us the sp hybridization for that carbon. Again, these guys do really follow that electron pair geometry. So basically 2 electron pairs is linear in terms of the electron pair geometry, and that should have a hybridization of sp. 3 electron pairs is trigonal planar, and 3 electron pairs would get you sp2 hybridization. 4 electron pairs is our tetrahedral, and that'll get you your sp3 hybridization. 5 electron pairs, which gets us to our expanded octet, would get you your triangular bipyramidal. And that again would be 5, so sp3d. Again, you can pretty much just count the letters, 1s, 3 Ps, that's 4, and a d, that's 5. And that's again 5 electron pairs, and 6 electron pairs, which would get us to our octahedral, going to be sp3d2 in terms of the hybridization. Again, literally count the letters as well. So 1s, 3 Ps, that's 4, and 2 Ds is 6. So I highly recommend don't overthink it. Yeah, it is pretty much that straightforward, and just do it that way, and you should be in good shape in terms of everything that's happening there. We also talked about different ways to sort of classify some of the bonds, and we talked about sigma bonds. And sigma bonds are pretty much every sort of single bond that you draw in a Lewis structure. So kind of the first line, if you will, that you draw for bonds in a Lewis structure will be a sigma bond. As we talked about, sort of what that really means is, again, those orbitals are sort of heading straight at each other and kind of smacking right into each other. And that area where they go head on, and that overlap area is where we're sharing those electrons and the bonding's happening. And that's different than a pi bond. So a pi bond, if you remember, basically develops from an unhybridized p orbital, really 2 unhybridized p orbitals. So as we go through these hybridizations, especially with sp2, we have 1 unhybridized p orbital, and that's just a regular old p orbital. That's like pz orbital. And then for sp, which is where we typically get our triple bond happening, we actually end up with 2 unhybridized p orbitals. And that would be something like your py and pz orbitals, again, unhybridized. And because they're unhybridized, they technically still have the regular atomic orbital sort of shape, like the figure 8 shape that we see with p orbitals. And basically what's the difference is in terms of the overlapping that's happening is this is side-by-side overlap. So these guys are kind of overlapping side by side, as we sort of talked about the other day, kind of with over and above and below sort of the plane of the bond there. And again, that's sort of where those electrons will kind of be shared with these orbitals kind of side by side overlapping. And those are pi bonds. So really the easiest way to sort of break that down, if you had to figure out how many sigma bonds you have, how many pi bonds you have, basically a single bond, one line, is going to be probably a sigma bond. If you have a double bond, it is made up of a sigma bond and a pi bond. So kind of the first line is a sigma bond, the next one is a pi bond. And if you have a triple bond, which again would be 3 lines, first one really a sigma bond, next two would be a pi bond. Question on any of that stuff that we sort of talked about last time? Yeah. So we're going to then talk about molecular polarity and how to sort of determine the polarity of the entire molecule. And again, in certain cases, that is different than sort of the polarity that we talked about previously about bond polarity. And if something is a polar molecule, what that means is it will have basically what is referred to as a dipole moment, and it'll have an overall dipole moment. And dipole moments are really represented by those arrows that we saw when we talked about electronegativity, and these sort of arrows just like this. And it means really the same thing as it does there. It points to the side that's more negative, and the guy that kind of makes like a positive sign on the back end here is the side that's more positive. So just so everybody's clear, when we're talking about polarity here, we're talking about the entire molecule as a whole. So taking every bond into account, everything that is there, the entire molecule as a whole, what we're trying to determine is there overall equal sharing of electrons? Are electrons pretty much distributed pretty much equally over the entire molecule? Or is there an area where there's a little bit more electrons kind of hanging out versus another area of the molecule? And the result of that is 2 types of molecules. And one would be a nonpolar molecule, which does not have a dipole moment. And basically, I don't want to say it's neutral, but that's one way you could look at it. It has pretty much equal distribution of electrons throughout the entire molecule, which means as a whole, there is no side that's more positive. There's no side that's more negative. It's pretty much neutral. You know, all the electrons are pretty much evenly distributed throughout the molecule. And that's different than when we do have a polar molecule. A polar molecule is one where there is unequal sort of distribution of those electrons in that molecule. There's a side of that molecule where there's a heavier concentration of electrons happening, and that's going to create a negative side in that part of the molecule, while the other side where the electrons are kind of going away from will create more of a positive side. So it is very different though in a sense than what we were talking about earlier when we were talking about electronegativity and differences in electronegativity values. And when we use electronegativity values, for the most part, what we're trying to determine is that bond polar, is basically what we're trying to figure out there. And basically what that means is the actual bond between these 2 atoms, are they sharing the electrons equally or unequally? And that does not necessarily always translate into whether or not the entire molecule is polar or not. The only place where it really does sort of translate okay into, well, it is going to be the same, is, as I might have mentioned earlier, it is in a diatomic molecule, because in a diatomic molecule, there pretty much is only one bond. So if that one bond is polar, the entire thing will be polar. And if that one bond is nonpolar, the entire molecule will be nonpolar. So if something does have a dipole moment, it would be represented by an overall kind of arrow pointing again in the direction is more negative and the other side more positive. If it doesn't, again, we would have sort of equal distribution of that. That's how you calculate the dipole moment. We're not going to really calculate it, but it's basically the charge and the distance between the 2 nucleuses. So let's talk about really the easiest ones to figure out whether or not the molecule is polar are nonpolar. And as I just mentioned, it is those diatomic molecules. And basically in a diatomic molecule, you pretty much only have two atoms. And because you only have two atoms, you pretty much have only one bond. So if we took something like H2, O2, which is double bonded, N2, which is triple bonded, F2, which is single bonded, all these guys here have pretty much just one bond. And if we took the difference in electronegativity of all these guys, because they're all the same element, hydrogen, hydrogen, oxygen, oxygen, nitrogens, and fluorine, we would all get a difference in electronegativity of 0, basically, if you went to that chart and you subtracted the two values. So 4 minus 4 is 0, I think. 2.1 minus 2.1 is still 0. And what that would tell us in each of these cases here, we have a nonpolar bond. And that really is what the difference in electronegativity is telling you. It's not necessarily telling you the entire molecule is polar or nonpolar, but it's telling you that in this particular bond between these two atoms, this guy is going to be a nonpolar bond. Now, because these are diatomic molecules, as I mentioned, this nonpolar bond that exists in all of them is the only bond in the entire molecule. And because the only bond in the entire molecule is nonpolar, each of these guys would also end up being a nonpolar molecule. So this is one of the places where bond polarity and molecular polarity will be the same. And that's a case where you have a diatomic molecule. So if that one single bond in there is nonpolar, then the entire thing would be nonpolar. Now, obviously, if we swapped out some of these things and we had something like HCl, HF, these are also diatomic molecules. These are what are known as heteronuclear. Heteronuclear means that there are two different elements involved, and that's different than homonuclear up here. Homonuclear is like homogeneous, the same throughout, so you have the same element on top. Here we have different elements, and if we did the difference in electronegativity values for each of these, again, what we would find is the chlorine in this case would be more electronegative, and the fluorine would also be more electronegative. So we could draw these bond dipoles, again, pointing to the side that's more negative, and the back end there that kind of makes the plus sign to the sign that is, or the side that is more positive. And what that means is these guys do have polar bonds. And those polar bonds is a result of that difference in electronegativity. And for the same reason as above, because that is the only bond that we have in the entire molecule, it must be also a polar molecule. So these guys are really the kind of super easiest ones to determine. And it's really because the molecule itself only contains one bond. So diatomic molecule is really easy. Pretty much just got to figure out, is the bond polar? And if the bond is polar, then the molecule will be polar. And if the bond is nonpolar, then the molecule will be nonpolar. By the way, this would be its dipole moment as well, this arrow, the way I'm pointing it. This is its dipole moment heading towards the chlorine, heading towards the fluorine in this particular case. Any questions on diatomic molecules? They're pretty straightforward, not too bad in terms of determining that. Now, if everything was that simple, that would be great, but of course it's life, so it's not going to be that simple. So when we do get 3 or more atoms involved, we do have to look at a couple of things here. What do I want to look at? We do need to look at whether or not the bond or the molecule has polar bonds. So once we have 3 or more atoms, we have to determine, first off, are there polar bonds? And second, once we determine whether or not there's polar bonds, we need to determine the actual, or look at the molecular geometry, or the shape. So it gets a little bit more difficult when you got 3 or more atoms together in a molecule. You have to look at those two things. Obviously, in order for it to be a polar molecule, you do need something that has polar bonds. And then you also need to take a look at its molecular shape to determine whether or not it actually is going to be polar overall. So let me actually find somewhere I could write here. So let's take a look at, for example, a couple of examples here. Let's take a look at CO2, which I think we have a prettier picture of later, but we'll look at it here. So if we look at CO2, this obviously has 3 or more atoms involved. So the first thing we want to really do is determine whether or not this guy has polar bonds. So again, you could look at the electronegativity table and the values, but you really don't need to, because if you look at the periodic table, and you take a peek at the periodic table there, this is the periodic table right there: carbon, nitrogen, oxygen, fluorine. And what we see is carbon and oxygen are in the same row, which means going this way, oxygen should be more electronegative. So you don't even need those numbers, that we saw previously. And if we were to draw the individual bond dipoles, they should be heading towards the oxygen. And this guy should be heading towards the oxygen. So first off, here we do have polar bonds. So you may say to yourself, it does have polar bonds, so should be a polar molecule. And we do have to investigate the second thing, which is, what is the molecular geometry here? And when we look at this, this has the carbon, has 2 electron pairs, has 2 bonds. So hopefully you know that the molecular geometry of that should be linear. It is essentially a straight line. So we have something with polar bonds. We have the geometry of this molecule, which is linear. And now we need to determine whether or not this is going to be a polar molecule or not. And to do that, if you just kind of look at like a pencil or something like that, like I'm holding here, if I take one side of it and pull this way, which is 1 oxygen, I take the other guy, pull in the other way, which is an oxygen, I am actually pulling on this as hard as I can, and my pen is really going nowhere. So although this guy does contain polar bonds, because of the geometry here, it is going to actually cancel each other out. And this guy will actually be a nonpolar molecule because of the geometry. And that is because when we draw these bond dipoles, these little arrows here are what we like to call in physics, I vaguely remember, but they call them vectors, I think. And vectors have direction, they have magnitude. And then I fell asleep, but I think I woke up long enough to remember that in certain cases, they add to each other. In other cases, they actually will cancel each other out. So when you're dealing with vectors, basically, if things are kind of pointing in equal and opposite directions, they will essentially cancel each other out. Or if they're kind of heading straight at each other in equal directions there, they will cancel each other out. So because this CO2 is linear, our dipoles are pretty much pulling equal and opposite of each other, they will actually cancel each other out. So CO2 is a very good example of a molecule that can definitely have polar bonds, but the overall polarity or molecular polarity of this guy is actually going to be a nonpolar molecule. So this guy is a nonpolar molecule. Any questions on that? Yeah, so the bond between carbon and oxygen, I found out, was polar through the electronegativity. So if you remember in previous chapter, we had that table of electronegativity values. You could go to that table and you could actually pull the actual electronegativity values. And when you're trying to figure out polar bonds, that was the one where we had like 0 to 0.4 is nonpolar, like 0.5 to less than 2 is polar, above 2 is ionic. But what I was actually saying is, if you actually look on the periodic table, this is the run of elements that you have in that first row. They're all in the same row, basically all same period. So even if you didn't have that table available to you, just by their locations, the carbon is further to the left than the oxygen. And because the oxygen is further to the right in the same row, you can make a pretty safe bet that the oxygen is going to be more electronegative than the carbon, and that's going to create a polar bond. So again, what I was saying is you don't actually need the values. You go find the values if you really want. But whenever you have two elements that you're trying to compare, is that bond going to be polar or nonpolar? If they're in the same row or period, the one that is further to the right will be more electronegative and probably will create a polar bond. And if they're in the same group, the one that is further up in the group will be more electronegative and probably create a polar bond. So sometimes you really don't necessarily need those numbers. You could just use the general trend on electronegativity from the periodic table to do that. And in this case, because carbon oxygen was dead on there in the same period, we really didn't even need to go look up those values to figure it out. Other questions on that? Okay. Let's see here. So when we think about sort of molecular polarity, sometimes people kind of think about it like tug of war, right? Pulling the rope, two teams pulling the rope. There's a little flag in between. And if everybody kind of pulls the rope equally, you know, the flag's not going to go anywhere, and it will be like a non-polar situation. If somebody's pulling the rope more on one side than the other, obviously the flag will go. And that's sort of the same idea also when vectors sort of head at each other. You could kind of think of that as like two people on opposite sides of a door pushing on it. That door is not going to go anywhere if they're pushing equally. And that's sort of the way sometimes people think about it. And now this is very different than, say, if we take another example, which is something, say, like water. And if we look at water and we draw the Lewis structure, all pretty like, I suppose. If we want to look and see if we have polar bonds here, again, if you went to that sort of table and you looked up those values between oxygen and hydrogen, oxygen is more electronegative. So we would have polar bonds heading in this direction towards the oxygen. And so for water, the answer is yes, we do have polar bonds, which is not bad. Now, the second thing we do want to look at is what is the molecular geometry here of water. And we have 4 electron pairs and 2 bonds. And 4 electron pairs and 2 bonds is bent or V-shaped. And bent or V-shaped is this geometry, which is kind of why I drew it this way. So unlike sort of the previous one, we pretty much have kind of like a triangle V type of situation. And you got a polar bond kind of heading toward the top. You got a polar bond heading the other way. You could almost imagine they're both going to kind of meet up at the top. And if you think of it as being like on a string, if you just pull directly from the top, you could kind of imagine the whole thing would pull up with you. So since they're both kind of heading this way, they're going to kind of meet and pull up. And what we end up getting in this case is a net dipole moment happening on this molecule heading towards the oxygen. So this is our net dipole moment. And what that basically means in water, water is going to be a polar molecule, where in the case of water, the oxygen side is more negative. The hydrogen side is more positive. And I'll do it for old time's sake here. The old adding vector thing, I'll try to remember. But we got one vector going this way. When you add vectors, you draw them like head to tail there, or point to tail. So that's that vector. This other vector would be heading out this way. And they netly join coming this way, which is why the overall guy is heading in that direction. And again, that is the part where I fell back asleep in physics, but I think that's about right there. It's been a while. But so what we get is when these two guys, again, come together, we get that net dipole moment heading in this direction, which is represented here. Question on that there. So sometimes people, you know, let's be honest, we don't want to draw all these things or think about these things in three-dimensional space. It makes our heads hurt and all that kind of stuff. So of course we want a more easier way to do it. So an easier way to do it sometimes is what is sometimes referred to as symmetrical geometries and unsymmetrical geometries. So we could kind of use symmetrical and unsymmetrical geometries to sort of help us decide whether or not something is going to be polar or non-polar. So when we think about symmetrical geometries and when we think about sort of unsymmetrical geometries, we have some symmetrical geometries. And some symmetrical geometries are trigonal, planar, and we're talking about molecular geometries here, so not electron pair, but overall molecular geometries. Tetrahedral, triangular, bipyramidal, octahedral. And what all these symmetrical geometries have in common is, if you remember what they look like when you drew them, is that they have no non-bonding electrons on the central atom. They pretty much have all bonding electrons. So if you draw a Lewis structure and you have no non-bonding electrons on the central atom and everything attached is the same element, it is a pretty safe bet for you to write down that is a nonpolar molecule without having to really think any further than that. So again, nothing in life's 100%, but probably 99% of the time, if you draw your Lewis structure and you see no dots on the central atom, you see everybody on the outside is the exact same element, it is probably a very safe bet to go, that thing is a non-polar molecule. And that's because that's going to get you pretty much symmetrical arrangement of all of the atoms, and they're all going to be equal and opposite of each other. And that means when they pull or push, they're going to pull or push equal and opposite of each other. So for example, if I took, let's go with CF4, and I won't draw all the dots on the outside just for making it not too busy looking. But if we look at this, this does have polar bond between carbon and fluorine. Fluorine is definitely more electronegative. So if we drew the bond polarities, it would be all these arrows heading towards the fluorine. So this guy does have polar bonds. The geometry here is 4 electron pairs and 4 bonds, which is tetrahedral, would be the molecular geometry. But honestly, I don't even need to do any of that, because I could just look at this Lewis structure and go, there is no dots on my central atom. Everybody that's on the outside is exactly the same. This is going to be a non-polar molecule. And that is because, again, I won't attempt to draw it correctly in three-dimensional space, but if you drew this guy in three-dimensional space or solid in three-dimensional space correctly, all 4 of those fluorines are equal and opposite of each other, and they will cancel each other out. So again, it's like 4 guys pulling on 4 corners equally on a rope. Again, the rope is just going to kind of get tight in the middle, and nothing's going to happen. Nothing's going to move because everybody's pulling equal to it on the outside. Question on that? Now, what would happen if I had pretty much the same deal with my fluorines, but I decide, hey, I'm going to swap out a fluorine for a hydrogen in this particular case. So now when I draw my Lewis structure, I got no dots on the central atom. I still have my polar bonds heading towards fluorine. Remember, based on electronegativity, technically speaking, this bond right here between carbon and hydrogen is nonpolar, right? So what we have now is 3 of these guys kind of pulling this way, and this bond over here going, well, I'm not really pulling the other way. And it actually, and believe it or not, even though it's nonpolar, it actually is a little bit more electronegative towards the carbon. So in addition, he's actually not pulling the other way. He might be even pulling with them. And you could kind of imagine if everybody's kind of pushing that way, the whole thing is going to basically move, and it will become now a polar molecule in this particular case. So if you have no dots on the central atom, everybody attached is exactly the same, it will be probably a nonpolar molecule. But if you take one of those bonds out and switch it out to another element, it will most likely go from nonpolar to polar in that case. Question on that. So those are sort of our symmetrical geometries. Our unsymmetrical geometries are pretty much everybody with dots. Yeah, so if you draw your Lewis structures, you got all those guys with dots. Let me get somebody here. So your unsymmetrical geometries is something like trigonal pyramid. You got your angular. You have your bent or V-shaped. You have some of those other ones that we saw in the expanded octet, your square pyramid. Seesaw. There we go. So these are some of the ones there that are going to be unsymmetrical ones. And again, what they all have in common is when you draw your Lewis structure, you will see dots on the central atom. So we will have dots on that central atom. We'll try dots without the O. Dots on the central atom. And again, that is your non-bonding electrons. And if everything is the same on the outside, it is going to be a polar molecule. So if you draw a Lewis structure, you see dots on the central atom, you see everybody on the outside is the same, pretty safe bet to go with a polar molecule, and without any too much trouble, I think, on that.
I'm sorry, can you repeat that one more time?
Yeah, so if you, unsymmetrical geometries, pretty much when you draw your Lewis structure, if you have dots on the central atom, which means you have non-bonding electrons there, and all the elements on the outside, all the atoms on the outside are the same element, it's a pretty darn safe bet to say that that's going to be a polar molecule. And that's because with those dots, like we had with water, for example, with these dots on the central atom, we have these unsymmetrical geometries. We got these guys pulling this way. And really, these non-bonding electrons also kind of want to pull a little bit this way as well. So everybody's kind of pulling in the same direction. And you're not going to have equal and opposite kind of pulling or pushing. You're going to get somewhere where you have unequal sort of pulling or pushing, I guess is the way to look at it, because you really have the lack of those bonds. So without those bonds there, you have just those non-bonding electrons, which won't pull back the other way if it needs to. And it actually will pull kind of, away a little bit as well because they're non-bonding. So pretty safe bet if you draw something, got some dots, everything on the outside is the same, should be polar. And you pretty much don't have to worry too much about that. Yeah.
Okay. I'm sorry, but can you explain one more time why the dipole moment goes towards the oxygen?
The dipole moment in this particular case, because the overall dipole moment goes towards the oxygen because the individual bond dipoles. So really when we draw these little two arrows this way, these are really the bond dipoles. And those are based on really electronegativity, that difference in electronegativity values. And those are really the bond dipoles. And bond dipoles are really just vectors, like in physics. And when you have two vectors that aren't really heading at each other in equal and opposite directions, you could actually add them together. So this one I just drew here would be this guy here. And the other guy you would just put at the end of it. And what ends up happening is when you put both of those together, they technically will add together coming up this way. Yeah. So it adds
right, that vector addition.
Yep. And basically what that would end up doing is sending the overall dipole moment heading in this direction, where this side would be more negative, this side would be more positive. Yeah. When you kind of take both of those guys together, you can kind of think of it, this guy's coming this way, you kind of slide the guy coming on the right, to the end of it, and then you kind of add them together and it heads that way. Yeah.
Okay, and that's like that's more or less because of the electronegativity of oxygen, like it wants the electrons, say, more than the hydrogens.
Yeah. So if you went in back to that table, I don't remember what the value is off the top of my head, but hydrogen is like 2.1, for example, and oxygen's probably in the 3-ish type range, 3.5 maybe. And if you take the difference between that 3.5 and 2.1, that's a lot of math for me to do in my head, but I'm going with 1.4. And so that basically means that it's going to be polar, right? Because it's above the 0.4 sort of mark for it to be non-polar. Yeah.
Perfect. That makes sense. Thank you.
You're welcome. Other questions?
I had a question.
Okay. All right. So that's a pretty easy way to do molecular polarity. And again, I would recommend that approach than trying to figure it out in three-dimensional space, who's pulling who type of thing. It's probably the better way. I will say what that really leaves you is a couple of things that we do need to talk about in terms of this sort of general way of doing electronegativity. And one way is basically that leaves you in terms of molecular geometry. That leaves you pretty much linear as your one that you kind of do have to think about what's going on with it, because in a linear one, it's basically this arrangement. Now, in the case of CO2, like we saw, they could be heading in opposite directions. And when they are heading in opposite direction, they're going to basically cancel each other out. You could also have a situation where perhaps they're heading right at each other as well. That also would probably cancel it out. But it is potentially possible in a linear situation that when you do those bond dipoles, everybody is heading in the same direction, and that would be polar, right? So nonpolar or polar with linear is pretty easy. Just think about a straight line and a pencil. And again, if they're pulling opposite, they'll cancel. If one's pulling more in the same direction, is going to move, it will become polar. So that one's pretty easy to sort of determine. But I will say when we talk about the idea of looking at something that has dots on the central atom and determining whether or not that's going to be a polar molecule or not, there is actually two geometries that do have dots on the central atom, but are still going to be non-polar. So those two guys actually should probably end up back this way. And they are the exception to the octet rule. I'm sorry, or the expanded octet, I guess is a better way of saying that. Where did I put all that guy? Put those guys here. So if we take these two sort of expanded octet guys, and the first one that will basically have dots on the central atom, but still be non-polar in a certain situation is linear. And that is the linear that is this linear here. The expanded octet linear, this guy here. And that is because what happens in this linear 5 electron pairs, 2 bonds, is, as we talked about, the bond angle here is 180 degrees, which means if you have this linear, not the 2 and 2 linear, but the expanded octet linear, what you end up having is if these guys are the same, they're going to cancel each other out because they're going to pull equal and opposite the two x's. And if you even look at the kind of non-bonding electrons, they make that triangle type shape, which means even the non-bonding electrons are going to pull kind of equal and opposite of each other, and they're going to cancel each other out. So this is sort of one exception that you can have dots on the central atom and still be nonpolar. So linear, again, the 5 electron pairs and 2 bonds version of linear will end up being nonpolar if, again, both of those things are the exact same element in that case. The other one that can have dots on the central atom and become nonpolar is our square planar. And our square planar looks something like this, maybe. Just kind of go this way. And basically what we got is 6 electron pairs and what we got there is 6 electron pairs, 4 bonds. And it is pretty much going to be nonpolar in this situation because it makes a square, which means if all these guys are exactly the same and they're all pulling equal and opposites of each other, they are going to cancel each other out. And we even have 2 non-bonding electron pairs, which will also go kind of equal and opposite of each other as well. So these are 2 exceptions to what I said earlier. These 2 guys will have dots. All right, dots, do you remember? Around the central atom. And if these guys are there and they have dots and they're still, everything attached is the same, it will be, again, nonpolar. Question on that. So that is sort of the easiest way when you're dealing with 3 or more atoms to sort of figure out polarity or not. And I would highly recommend you do it that way. Yeah. Any questions on that? Okay. And I scribbled on everything. I think that's pretty much what we were going over there. All right. So let's take a look at some prettier examples. Maybe I didn't write all over here. So we have our HCl bond here. And again, that's a diatomic molecule. So as we talked about, that's going to be really easy to sort of figure out. Again, this one bond here between the hydrogen and the chlorine is going to be polar based on electronegativity difference. And since, again, that is the only bond in that entire molecule, we would expect the entire molecule to be polar. I don't know if it's coming up very well in here, but usually a more reddish sort of color means that it's hot in terms of electrons. A more blue color over here means it's kind of cool, not so many electrons. So that's what sort of an electron distribution sort of picture looks like. Again, here showing all the electrons coming this way and making our partially negative charge over there and our partially positive charge over there. Again, those diatomic molecules are super easy because there's only one bond. So if that bond's polar, the molecule will be polar. If that bond's nonpolar, it will be nonpolar. Here's our CO2 example. Again, although it has polar bonds, the overall molecule will be nonpolar, and it is because of the geometry here. So basically a straight line. So you got this guy over here pulling this way. You have this guy pulling pretty much equal and opposite of each other. So they pretty much cancel their contribution. And as you can kind of see here, kind of equal distribution of those electrons over the entire molecule. And that's basically what a nonpolar means. There's no positive side. There's no negative side. We got kind of perfect equal sharing over the entire guy. And there's our water where we're adding it together, as we talked about in a couple of examples. Again, when these vectors come this way, because of the geometry, we get the net dipole moment, which is represented by this arrow. And that's why when we talk about water, we always say that the oxygen is more negative. The hydrogen side is more positive in that particular case. And again, as you can see here in this sort of diagram, a lot redder up on top where the oxygen is, which means there's a greater amount of electrons sort of happening here. a lot more blue towards where those hydrogens are, which means that the electrons again are traveling away from that bond. So NH3 here, for example, NH3 would also be a polar molecule. So if we drew NH3 in our Lewis structure form, again, if it was me, I would draw this and go, I see dots, I see everything attached is the same. I'm good to go with polar molecule. And this would be a polar molecule in this case. In this case, as you can see here in the prettier picture, the nitrogen is more electronegative, so our arrows are heading towards the nitrogen. And what's up here is our non-bonding electrons, which again, we have basically all three of these guys in this pyramid shape kind of heading upwards. And we have these non-bonding electrons maybe helping out a little bit as well, pulling in that direction. So again, you could kind of imagine all the electrons coming in to the top of it. And if you think about it like the string example, if you kind of pull upwards, you could kind of imagine the whole thing moving, and that would basically make it a polar molecule. Question on that there?
I had a question about shape versus geometry.
Yeah.
So would that last one, NH3, be considered tetrahedral, but be trigonal pyramid geometry?
Yeah,
or would you just pick one?
So we talked about two different types of geometry. One is what's known as electron pair geometry. And the electron pair geometry describes not the overall sort of shape of the molecule, but it describes how those electron pairs are basically sitting around that central atom. And in terms of the electron pairs around the central atom, it is sitting around, because it has 4 electron pairs, it would be tetrahedral for the electron pair geometry, or electron arrangement, sometimes called. Now, because we have those non-bonding electrons, what ends up happening is the actual molecule itself, because it doesn't have a 4th bond happening here in a traditional tetrahedral arrangement, because it doesn't have that bond, it allows the actual bonded atoms to really kind of move a little bit more than they would if there was that 4th bond there. And what it ends up doing to the overall shape of the molecule is give it that pyramid shape on the bottom, along with the triangle shape sort of up on top. And that's why the overall molecular geometry, which is sometimes referred to as the shape, is known as trigonal pyramid. So if you were asked what the molecular geometry of this guy was, or the shape of it, trigonal pyramid is the correct answer for that.
Thank you, that makes sense.
And that's why when we were talking about sort of geometry, when you do not have non-bonding electrons on the central atom, both the electron pair geometry and the molecular geometry name are the same. And that's because if this was, pretend 4 electron pairs and 4 bonds, with that 4th bond there, it's going to lock out the movement of all these other guys as it would without it there. And what you end up getting is the same shape that occurs with all 4 bonds and all 4 electron pairs, because they're all bonding electrons in that sense. And that's why when you look at those two names, they will always be the same if there's no dots on the central atom. And that's because pretty much what you're looking at is the same type of electrons all the way around. They're all bonding electrons. So they all end up in the same shape. It's only when we take off a bonding electron and put on some non-bonding electrons that it gives those other bonds a little bit more room to move around. And what that ends up changing is, again, the overall shape of it, or the molecular geometry name.
So if we had NH4, that would be non-polar, because it would all be going towards the hydrogen?
Yeah, so if we had NH4, first off, in terms of geometries, it would be tetrahedral for both, tetrahedral for the electron pair, and it would also be tetrahedral for the molecular geometry. And in terms of molecular polarity, the answer is yeah, because we would have no non-bonding electrons here. Everything on the outside is the same. So technically speaking, what's going to happen here is everybody is going to be pushing in, equal and opposite of each other's. This is obviously not drawn correctly tetrahedral, but everybody basically is going to end up being equal and opposite, and they're all going to be pushing in. So it's kind of like the door example. If you have 2 people on opposite side door pushing equally, Thor's not going to go anywhere, right? It's kind of just going to stay where it's at. And so they're all going to cancel each other out. So most people would go with this is going to be nonpolar based on geometry as a nonpolar molecule because of that.
Sorry for stopping you, but I appreciate it.
No worries. That's what I'm here for, to answer your questions. No worries.
I had a quick question.
Yeah.
So is it only going to be molecules that have like hydrogen on the outside that the pole is going to be towards the center? Because isn't the most electronegative going to be on the outside except for hydrogen?
Right. So in most cases, I won't say 100% of the time, but in most cases, if hydrogen's on the outside, obviously it's going to be pushing in. Just trying to think. I guess potentially possible you could have two different elements other than hydrogen on the outside that could kind of push in, depending on it. But in most cases, like you said, the least electronegatives usually should be in that center, so it should be pushing out most of the time. So I would agree with you that hydrogen probably would be the only case where you kind of see it pushing in that case, yeah. Because if you do it correctly, I guess you could technically draw a Lewis structure incorrectly and not put the least electronegative in the middle, and you could potentially find a structure that could do that. But if you sort of draw a correct Lewis structure, like you said, the least electronegative should be in the center, which means in most cases, it should be pointing outwards if there's a difference in electronegativity, with hydrogen being the only sort of exception to that. Other questions? Okay. All right, let's see here. So molecular polarity does affect things like solubility. It affects how things interact with each other, and we'll talk about it in a later chapter. But if you do have a polar molecule, basically a polar molecule has a positive side and a negative side. And if something is a polar molecule and has a dipole moment, what that means is no matter what the situation is, it is always going to have that separation of charge. And that creates a certain type of what's referred to as an intermolecular force, which is known as dipole-dipole interaction. And basically what that means is when you get a polar molecule next to another polar molecule, the other polar molecule is going to align its positive side next to the negative side, and they're going to have a way to interact with each other really well. And that's also why something like water is really good solvent, a good thing to dissolve things in, especially ionic compounds, right? Because when ionic compounds go for a swim, they break apart into a positive and negative guy. And what helps something that's ionic dissolve in water is because water is polar, the oxygen side of water will surround the positive side of that positive ion. And with the negative ion, the positive side of water will surround the negative ion. And what that does is when you take something like sodium chloride and put it in water, the ions get surrounded by water. And to our eyes, it looks like, wow, the sodium chloride just disappeared. It's gone. But it's really not gone. It just gets gobbled up by all these waters, and you can't really see it. And that's a really good way an ionic compound can dissolve, because without the water there, so for example, if you had the situation and you heated it, all the water molecules would then evaporate, and then there will be nothing to stop the positive and negative guy from coming back together, and you would typically see that solid reform. So for example, if you ever dissolve salt water in an experiment in chemistry, sometimes they do those experiments, you put it up on an evaporating dish and you heat it, and all the water evaporates, you're left with a residue of white solid in there if it's sodium chloride. And that's because when you heat it, you got rid of all that water molecules, and now the two ions, which are extremely attracted to each other, have nobody get in their way, and they come back together, and you see the solid reappear. That's why when we dissolve something, it is technically only a physical change, because the salt's still there, even though we can't see it. We could actually evaporate off the water and still see it. That's also why when you mix water and oil, they don't mix very well together, because oil is pretty much nothing but carbons and hydrogens together. And as we know, carbon and hydrogen is a nonpolar bond. And now that we kind of know what nonpolar means, we basically have a water molecule that has a fixed charge, and we have a nonpolar oil molecule that has no charge. they have no way to interact with each other. All really molecule-molecule interactions, which are intermolecular forces, they're all the basic interaction of a positive guy and a negative guy coming together. And with these two guys, they really have no way to interact with each other over the long period of time. For a very short period of time, this guy can temporarily gain a charge and have a way to interact, but those electrons will move back around and they'll break apart. And that's why if you ever mix something like oil and water or oil and vinegar salad dressing, right? For a short period of time, you could get all the mix, right? But if you leave it alone, what's going to eventually happen is the oil part's going to go to the top, the water part's going to go to the bottom, or the oil part and the vinegar part, right, will separate out from each other. And that's because for a short period of time, which is we'll talk about when we get there, dispersion forces, they're able to interact for just a little bit, but eventually over the long period of time, they have no long way to continuously interact with each other. Any questions on that there?
Yeah, so is the reason the oil is going to the top because the water is squeezing it in a way, like trying to get back to each other, or is it density, or is it both?
Yeah, it's a little bit of both happening there, but it's actually the density a little bit more than that. The oil is a little less dense, so it'll kind of float to the top, but some of that interaction as well. So usually whenever you have sort of the water and oil sort of mixture or something like that, water is usually the bottom layer for the most part because of density and stuff like that. It'll separate out. Like that experiment 3, I think it was, when they had the halogens and stuff like that. That's why they put the hexane in there. Hexane was nonpolar. And the sodium chloride solution, the sodium bromide solution, that was aqueous, or really like a water layer. And then when you put that hexane in there, that's why when you put the chlorine water, for example, the Cl2, which is nonpolar, would end up in the hexane layer, because this guy is nonpolar and this one's nonpolar. So they interact really well with each other. So they interact very well with each other. And that's why in that sort of experiment, if you remember, the chlorine started out up here in the hexane layer because it mixes really well, and not really down here in the aqueous or water layer. And they were definitely separated out and stuff like that. And that's sort of the same idea with like soap, for example. Soap, in case you're not curious, or maybe you're not curious, but in case you don't know, I guess is what I was trying to say there. This part of it is really just carbons and hydrogens. So the black is carbons, these guys are hydrogens. And this long chain of carbons and hydrogens is nonpolar. And usually at the end of soap, you have something like this group, as you can see in the picture there. This is a polar part. So soap has kind of two parts to it, has a polar part and a nonpolar part. And really the nonpolar part works really well with dirt. Dirt is typically nonpolar. So this carbon part pretty much traps the dirt. And what it does is it arranges itself in a way that the polar part of soap is on the outside. And that's a really good thing, because once it traps all your dirt, and usually once you soap up, you usually then use some water there, right, to wash it off with. So the water and the polar part of soap mix really well. So when you wash, off goes the soap, the dirt, and you're clean and happy. There's that life lesson of how to use soap properly, I suppose. Yes, so there you go. Any questions on that? All right, so let's take a look at these couple guys here. Why don't you take a second and figure out, are these guys going to be polar or non-polar molecules? So electronegativity values, I think, are given on the left there. So see what you come up with. So what we're looking at here is, overall, is this molecule going to be polar or non-polar? Okay, so let's take a look. So in this particular case, we have dots on the central atom. We don't have the same guys on the central atom, so we might want to investigate a little bit. Let's first talk about, are there polar bonds? So we do have our electronegativity values given to us. So nitrogen is 3, oxygen is 3.5. So if we take the difference between nitrogen and oxygen, we got 3.5 minus 3. So that is a difference of 0.5, which means that is going to be a polar bond. So we would head towards the more electronegative, which is the oxygen. Now between nitrogen and chlorine, they are both 3, which means this is actually going to be a nonpolar bond between the nitrogen and the chlorine. So we do have polar bonds like we talked about. We do want to maybe think about what the geometry is here. So we want to look at the central atom. Central atom has 3 electron pairs. So 1 electron pair here, 2 electron pairs there, and 3 electron pairs there. Again, double bond counting as only 1. And in terms of bonds, it has 1 bond to the chlorine, and again, double bond only counting as 1 towards the oxygen, gives us 2 bonds. So 3 electron pairs, 2 bonds. The molecular geometry of this guy is angular. The electron pair geometry of this guy is trigonal planar. But the overall geometry shape of it is angular. That means if we kind of draw it in its sort of proper sort of way, it will look something like this. And we basically have a dipole going this way. So again, if you just think about it, the only thing that has a dipole is kind of like pulling on one end down. So you figure if you take something that's like this and you pull one end, you could kind of imagine the whole thing moving with it. And this guy then would be a polar molecule.
So if you had multiple of those molecules, would only the oxygen and nitrogens be interacting and chlorine would just be a bystander?
Yeah, so in this case, overall, if you're talking kind of like what we were talking about just a second ago with a molecule, what this means is the overall dipole moment would be heading, towards the oxygen, which means the oxygen side would be more negative. This side over here would be more positive. So between the two, the oxygen would probably interact with something that's positive. Potentially the nitrogen part here could interact with something that's negative. And the chlorine probably for the most part would probably sit it out. Probably not do too much interaction happening in that area of the molecule. So because really everything is sort of happening here between the nitrogen and the oxygen, this is probably where you would see the greatest sort of unequal distribution of those electrons, and it would be more negative towards that oxygen side, where it would probably mainly interact with something positive, and the nitrogen would interact with something negative. And like I said, probably not too much in most cases happening over here. Other questions on that? Okay, so let's take a look at the sulfur oxygen here. So again, we do have some electronegativity. If we take sulfur and oxygen, the difference in electronegativity of those two guys is 3.5 minus 2.5. That's a 1. So that definitely is going to be electronegative, again, heading outward. And we do have polar bonds here. We do want to look at the geometry. So we have 3 electron pairs. Again, 1, 2, and 3. And we also have 3 bonds, same ones, 1, 2, and 3. So 3 electron pairs, 3 bonds is trigonal planar. And basically that is a nice symmetrical arrangement, as we talked about. Really, if you looked at the Lewis structure before, I drew all over it. Basically, there's no dots on the central atom. Everybody on the outside is the same. This is going to be nonpolar molecule. Question on those there. Okay. So let's see here. Why don't you try a couple here and see let's see. Why don't you think HCN, CCl4, we'll do this guy. Oh, formaldehyde. Let's do BF3 that we saw earlier. Let's do all right, so decide whether these guys are polar, non-polar. See what you come up with. We'll do a couple other ones that we did earlier. All right, so figure polar, non-polar molecules on these guys. See what you come up with. What an extra one we did as well earlier.
What do you want us to do with all these?
I want you to decide whether these are polar or non-polar molecules.
Should we look at our electronegativity chart to figure that out?
You can, but you probably don't need it. So you could probably just try the approach where we did, you know, what the Lewis structure looks like. Are there dots, no dots? You'll probably be okay.
Okay, thank you.
I'll help you out. Let me draw the Lewis structure for you for these guys. There we go. So it looks something like this.
For like later purposes, what is it called when you're trying to figure out what's the most optimal structure?
I think you're probably talking about using formal charge to decide what would be a better structure.
Yeah, formal charge. Thank you.
Yeah. So in terms of bent or angular, they do technically kind of mean a little bit different because angular is more of a bond angle around 120 degrees, a little less than that. And bent or V-shaped is a bond angle around 109.5 or a little less than that. So they technically do mean something different, although some people will, for 3 electron pairs and 2 bonds, go with bent for that one, or they'll say bent angular. Usually they use something to do with angular in there. And again, that just gives you an idea that we're talking more about the 1/20th angle rather than where we're talking about bent or V-shaped like water, which is 4 electron pairs and 2 bonds, where we're talking more like 109.5. So technically speaking, there is sort of a difference in terms of the bond angle of those two, in terms of where they end up. So for our class, we'll go with angular for 3 electron pairs and 2 bonds, and bent or V-shaped for 4 electron pairs and 2 bonds. I do know sometimes people for the angular one will kind of interject the bent aspect of it, but it does technically sort of mean a slightly different bond angle. All right, so since we're getting to the end, let's take a look at these, and I'm going to show you how quickly I'm going to go through these. And I'll probably be right most of the time here. So we'll go quicker through the rest of them, but let's take a look at this first guy here. There is a polar bond between carbon and nitrogen. And again, you don't need the values to determine that. If you look at the periodic table, carbon is right next door to nitrogen, and nitrogen is further to the right, which means nitrogen should be more electronegative. And carbon and hydrogen is essentially nonpolar. And the geometry here is 1 electron pair, 2 electron pairs, 1 bond, 2 bonds. And this is linear, which means basically a straight line. So we are going in this direction towards the nitrogen, and this guy would be a polar molecule. All right. So now for the rest of them, I'm just going to jam through them because, you know, this is how you should do it, I think. Yes, this is how I would do it. I would look at this Lewis structure and go, I see no dots. I see everything the same. I'm going to go nonpolar on that, and I'm probably going to be right. Yeah. I'm going to look at this guy and see no dots on the central atom, but I don't see everybody the same. And that's when that nonpolar guy becomes a polar molecule because of that. And the real polar part of this is the carbon-oxygen bond. That part is polar right there, heading towards oxygen. I'm going to look at this guy and go, I got no dots. I got everybody the same. That's going to be nonpolar. And it is nonpolar because the geometry here is trigonal planar. That's our triangle view. Everybody's equal. I'm going to go this guy and go, I got no dots, but everybody on the outside is not the same. I'm going to go with polar molecule. The real reason is, again, they're all going to be heading towards chlorine, and our fourth guy is not going to be going the other way. He's actually going to probably be going with them, and we're going to get net movement to the right there. I'm going to look at this guy and go, I got no dots. I got everything on the outside the same. I'm going to go nonpolar on that guy. And the longer reason is triangle, same idea. Everybody's pulling out equally. I'm going to look at this guy. I see dots. I see everybody the same. I'm going to go polar. And again, here we are going to have polar bonds heading in this direction and this direction. But again, this guy is angular, almost like water. So in this case, they are actually going to add heading this way, yes, in terms of overall. And lastly, I see dots. I see everything the same. I'm going to go polar molecule on this guy. And you can see I just ran through that polarity in like 2 seconds. And I would recommend doing it that way as well. Don't overthink it. Bad things happen when we overthink. Yes. Question on how to assign that molecular polarity. Yes. And literally,
I just wanted to know why there's. Oh, I'm sorry.
No,
I just wanted to know why there was no dipole moment between hydrogen and carbon.
they're technically not, because if you do the difference in electronegativity, let me get a cleaner page maybe.
Is it because hydrogen's higher than carbon?
Yeah, if you actually
balances
if you look at the values, I believe this is 2.1. This is like 2.5. So when you do the difference in electronegativity, that's 2.5 minus 2.1. That gets you 0.4. And the cutoff for nonpolar is 0.4. And the reason it is that is because of this bond, because all organic molecules are pretty much carbon and hydrogen, and they're nonpolar. And that's sort of why the cutoff is. So even though this is considered nonpolar and equal sharing of electrons, in reality, if you look at the carbon-hydrogen bond, there's a slight unequal sharing of those electrons, right? So it's really a little bit more unequal heading towards the carbon, but it's not to a point that people in the chemistry field, I don't know, chemistry field, I guess, that they consider it unequal sharing. So the overall idea of it is technically it's equal sharing, but the reality of it is it's really not equal sharing. The only true place where you get equal sharing is if you hit something with a difference of 0. Then you really do truly have perfectly equal sharing of those electrons. Anything above 0 to like 0.4, it's still technically considered equal sharing and nonpolar, but in reality, there is a slight difference in electronegativity, which means the electrons here are going to feel a slight pull heading towards carbon. But again, in terms of chemistry lingo, is not enough pull to be considered polar. So it's still considered nonpolar. So yes and no to your question. There really is a slight difference in those electrons, but it's considered nonpolar. And that's why you usually wouldn't draw the arrow. Some people do, but usually most people won't draw the arrow for it because it's technically considered nonpolar.
Great, thank you.
All right, well, that wraps up that funness, yes, and this chapter. So we'll start at 7:15, and today's lab is this, yes, so it's all this. So we'll talk about the study assignment, and I think we covered all the material in the study assignment, and it will be due, I think, today. So, you know, if you want to start working on it, you can now. Again, the study assignment be in the back of your lab manual. You know, it's pretty much all this stuff. We'll just go over just to make sure you know what to put in each little box. But then that's pretty much it. So I'll see everybody in about 15 minutes. Make sure you put here if you haven't done so, and I'll see